All right, so not only are those tests trying to target your math abilities, but they're trying to target your attention to detail, okay? Because the ACT is like a college readiness test, right, to see how well prepared you are for college, how successful you're going to be at college, and one of them, and even the workforce, the military, that kind of stuff, okay? And then, of course, exams kind of target the same ideas. If I'm going to be good at my job, then I got to be pretty detailed, right? I got to pay attention to detail. If you are in any profession and you are just going to work and you just do the job and you just do it just to get stuff done, you're probably not a very good employee, and your boss probably doesn't like it because you're just doing things to get them done, okay? And don't really care maybe whether I'm doing things to get them done the right way. Does that make sense? But if you're paying attention to detail, you're getting things done efficiently, you're getting them done right, okay? And you're probably a good employee, all right? So those are the things that those tests kind of try to gauge as well as your mathematical ability. So what they try to do, knowing that the authors of these tests know that you have some like psychological tendencies, things that you inherently want to do, whenever people see the word list, automatically in their mind, probably 90% of the time, if not more, they automatically start with the idea of smallest to largest without even being told. Does that make sense? I asked you to list something, and I didn't give you an order, and I asked all of you to do it. I doubt anybody's going to go largest to smallest, okay, if I just gave you a bunch of values. Does that make sense? Probably do smallest to largest. So the creators of these tests understand those things, and they want to test whether you're paying attention to detail. So what do? They play off that. They'll flip-flop those words and say list from largest to smallest. Is that all right with everybody? All right, so you got to pay attention. So you got to be very, very cognizant of that. Now, something that maybe isn't so much mathematical, but being able to kind of understand how testing and that kind of stuff is done and how our minds process things. Give you kind of a real-life situation here. If you guys have a car, we're in a gas station, right? In a gas station, go up the gas pump. We've got 3 buttons to push, correct? 87, what are those, 89 and 91, are those the numbers? Okay, and those just tell us some characteristic about the gasoline, right? 87 is unleaded, correct? Okay. Most of your cars are going to use it. Now, if your parents have like a Lexus or a Mercedes or a BMW or something like that, then it's going to tell them that they have to use premium, right? But probably 95% of the working society is going to have a car that is created off of the use of unleaded gas, okay? Does that make sense, everybody? We understand that? Okay. Now, if I put premium in my gas is unleaded in my Jeep. Okay. If you look at your gas tack on your fuel gauge, it will say what kind of gas you need to use. Mine's unleaded. Okay. That means that is kind of the bare minimum requirement. So I could put in 89. I could put in premium, and it'd be fine for my gas. Does that make sense? Okay, it would not hurt my car any. But if my fuel gauge says I got to use premium and I put 87 in it, it's going to have a negative impact on my car. Okay, it's going to gunk it up. Does that make sense? So if say 95% of us are always choosing unleaded, okay, gas stations, if we go up to the pump, you go to most gas stations, you're going to go 87, 89, 91. Okay, and I always go, so I can look at this, okay, it's always the one on the left. Always push 87. That's the only one I ever get, unleaded, unleaded, unleaded. Okay? And then I go to the gas station on the corner of Finley Road and Sugar Street. And it's backwards. Okay? The one there says 91, 89, 87. And what do they probably get a lot of people to do? Click the 91, and now they pay 20 cents more in gas than per gallon than what they wanted to or they needed to. Does that make sense? Okay. So they know that you have been trained, okay, to think that way, to think smallest to greatest, right? And then the creator of that gas pump, okay, said, I have a marketing tool here. I'm going to flip the numbers, okay, and now make money for that gas station. Does that make sense? Huh? It's just something to think about. Like, people are like, where am I going to use the math? And I don't know if you're ever going to use this triangle congruency stuff, okay? But some of the things that we talk about on the way to learning these, you might use and apply and see in everyday life, okay? When we start talking about triangle congruency, we're interested in showing two triangles congruent, okay? In doing that, and I think the best way to kind of understand these postulates and theorems is actually taking one triangle and kind of duplicating the information that we have in that one triangle and seeing what we get when we try to create a second triangle with the same information. Meaning that if I have like 3 pieces of string, okay, or 3 sticks, and they're different sizes, they could be the same size, it doesn't really matter, but I know that they're going to touch end to end to make a triangle, and I give them to you, okay? Now the idea is that if I have 3 segments, that one is a mile long, one's a foot long, one's an inch long, those are 3 different segments of 3 different lengths, right? They won't make a triangle. There's a relationship about the size of the segments that we have to use to make a triangle. But let's say that I give you 3 pieces of yarn, 3 pieces of string that I know will automatically or always, I guess, give you a triangle. Okay? And I tell you, put them endpoint to endpoint and create a triangle on your desk. Okay? And you look at that triangle, you bring that triangle's image in your mind. Now I ask you to scramble the pieces of yarn up or string up, and then reconstruct a triangle. With the same pieces, make another triangle. What is the relationship between the 2 triangles you just made? They're congruent. They've got to be the same, right? Didn't you use the same components to make them? Does that make sense? Okay. That's what the side postulate says. SSS stands for side, side, side. Because if 3 sides of one triangle are congruent to 3 sides of another, then the triangles are congruent. Or essentially, if I give you 3 sides of one triangle and ask you to deconstruct that, pull them apart, and then put them back together to make a new triangle, that new triangle is no different than the first one you started with. Okay? That's what the side, side, side postulate says. Now, you might be thinking, well, I can do that with anything. I do that angle, 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 side, side. You can't. Okay? There's only a few different types of collections or orders of parts that you can do that with and be guaranteed congruent figures. Okay? So I want to show you a GeoGebra here that I made that kind of maybe helps hit that home a little bit more. All right, if I start with that triangle in front of you, okay? And I don't even care that you guys know what the angles are. Let's say we don't know what the angles are of that triangle that I'm starting with. But I give you 3 segments, okay? 3 segments that are going to create a triangle. And I ask you to kind of take one of those segments and copy it. Okay, would you agree that that's a copy, that DL is a copy of AK? Okay, so those would be congruent, right? So right there you got a side congruent to a side. And I ask you to keep doing that. Do that with another side. Okay, would you agree that MK and NL are the same length? So you got SF now. You got side congruent to side, and then the second side congruent to the second side. Now understand that those 2 things are sharing a point, right? They're sharing the red one and the blue one over here on the right. They're sharing that point right there. And that's the only thing they're sharing. So these 2 things are going to float in 2-dimensional space. I could actually rotate. Think about this. I'm just going to put a circle in here real quick. Would you guys agree that that blue segment could actually rotate anywhere on that circle? Does that make sense? Okay, where my cursor is could be anywhere. So we could kind of change the angle that's between the red segment and the blue one, right? But still have those 2 segments being congruent, so that the 2 segments of the original picture. All right, so that being said, we could have that, but now what happens if I bring in the 3rd piece of string or the 3rd stick or whatever, and I now tell you that your blue one and your red one have to terminate at the endpoints of that black one, right? Does that make sense? So the endpoints of the red one and the endpoints of the blue one have to be the same as the endpoints of the black one. Is there one and only one triangle that can be created in? Okay. Now, what did we find? We every time that I got to like a K value of 1, 2, or 3, it showed you these segments being congruent, right? Did we ever talk about angles? Never talking about a single angle up there, right? When I look and check out the angles there, you got 64.15 and 87.98 and 27.87. I never, ever, ever worried about angles in creating this figure over here. Look what angles show up when I just focus on the side lines. Does that make sense to everybody? Okay. So what's the conclusion from the side postulate? The conclusion is that we have triangles congruent. Well, what's one more step from that? If I have triangles congruent, aren't all their corresponding parts congruent then? Well, think about what we did to get side. We knew everything about the side lengths, right? We knew 3 sides congruent to 3 sides. Didn't know a single thing about angles. But now that the triangles are congruent, now we know all 3 relationships about the angles, which angles are congruent. Is that all right with everybody? Okay. Now, if I wanted to name these, let's name this one. We want to name this one on the left. You can't. James. What letters we got here? Okay, so K-A-M. Okay. Congruent to, now I don't have them over here, let's just call them A, B, and C. Okay. So if I did that, okay, now K, now how do I figure out what letter K matches up to? I look at the segments that K is between. K is between the segments that have 2 marks and 1 mark, right? So I come over here and do the same thing. 2 marks, 1 mark, what's between them? B. So K and B have to match it. They have to be the first. Okay? This idea of using the markings is going to be a nice tool for you when they're not direct, like copy and paste translation. Then I went to A. A is between no marks. I guess it would be, for some reason it doesn't show up. That's 3. 3 marks and 1 mark. So over here, 3 marks and 1 mark. So I got to go to C and then A. Okay, maybe I should call that A prime because they're different. They should be different. I didn't think about using A twice. They're different letters. They're different. And now, if that's true, if I could show those 2 triangles congruent, do we know that K is congruent to B? I look at angle K, it's 87.98. Is that the same thing as angle B? 87.98, right? Is A 27.87 and C 27.87? Is M 64.15 and A prime 64.15? Okay. So those are the conclusions that we get once we say that these 2 triangles are congruent by side. All right. Is that all right with everybody? Does that make sense? Talk about one more theorem or one more postulate, but there's a vocabulary word that needs to go with this. Okay, and included. Okay, the word included, and we're going to talk about included angles, included sides. Okay, I know Canyon, this would be weird, but let's say you were invited to a party. Okay, you would be included, right, Canyon? Okay, so being invited to something, included in something means I'm amongst everybody else, right? I'm within everybody else, okay, and within their activity, okay. So when I talk about included angles, okay, they're the angles that are in the midst of everything else, and those everything else are going to be 2 sides, okay. So an included angle is the angle that is between or within or is created by 2 identified specific sides. Okay? An angle that is included is the angle that is between or within or created by 2 specific sides. If I look at that picture there, AB and BC are my specific sides, the sides that I know information about. What angle would be included or between or made by those? So if I'm looking at this segment here, AB and BC, the ones that have the marks in them, what angle would be between them? Angle B. Angle B is referred to as an included angle. Okay? If we have included angles, we should have non-included angles. You see, angle A is not between those 2 sides. So angle A would be a non-included angle. Angle C would be a non-included angle. Is that all right, everybody? If I look at that picture, what's included? What angle is included? Angle O. Angle M and angle N would be non-included. Okay? So why is that important? Because I look at this. I don't even read it yet, but look at SAS. Is A between the two S's. So it's included. Does that make sense? So it's between S and S, between two sides. It's included between two sides. So in my description of my postulate, we should have, and in my picture, we should have an angle that is between two sides that we have information about. Okay? The angle is sandwiched in the middle. Where it says the two sides and the included angle of one triangle are congruent to two sides, the included angle of another triangle, then the triangles are congruent. The picture that you usually get is something like that down at the bottom. Okay? Tried it in the PowerPoint to give you kind of the most generic way you're going to see these pictures. Okay? We have side angle side in the picture on the left, we have side angle side in the picture on the right. All right, so again, going back to, I think the best way to kind of visualize these is to, let's just say that I gave you a piece of string, maybe a piece of cardboard that has an angle kind of cut out in it, and I give you another piece of string. And I ask you originate those or orientate those so that you have a string followed by an angle followed by another piece of string, and look at the triangle that's created. And I ask you to disassemble them and repeat the process. Is the set of two triangles that you just created the same or are they different? They should absolutely 100% of the time be the same. Okay? Now why? Can't prove postulate, can't prove it, but let's see a picture of this. Not that one. Should probably have a few more of these open. There we go. All right, so here's the idea, okay? And the way I've got this set up, it's going to provide maybe a little bit of a different orientation of the two triangles, but we should still be able to see that they are indeed congruent. So what I'm going to do is I'm going to take that blue stuff, I'm going to take the dotted segment, okay? And I'm going to move it down there, okay? Do you see that the two dots, the two blue segments that are both 2.71, right? So that's a side congruent to a side. Now I'm going to pull that angle. I'm going to pull that angle and we'll put it right there. Okay, would you agree both those angles are 81.07? So you got side congruent to side and angle congruent to an angle. Now, the way this is kind of set up here is that this angle here is defining where my ray has to go, right? For my angle, my other side. So we'll take this black line down here, and I'm just going to line it up, lay it right there. Okay, so it matches up to the edge of that angle, right? Does that make sense? So would you guys agree that those two segments are congruent? 6.13. So we've got a side congruent to a side, followed by an angle congruent to an angle, and a side congruent to a side. That is going to define B prime and A prime. What can I do with those two things? I can connect them, can't I? And when I connect them, look at what it gives me for the distances of AB and A prime, B prime. They're the same, aren't they? Look at the other two angles. One of those angles is 73.83. Is this one 73.83? The other one is 25.1. Is this one 25.1? Okay. So the idea here, using those components, and I don't know if I can do this. See if I can. If I do that, okay, maybe not great, but you can see that they do two different triangles, right? They overlap each other, correct? Or perfectly, right? Okay. So hopefully that maybe convinces you that using those parts, using a side, an angle, and a side in those relationships, we do indeed get congruency. Okay? What I want you to understand, and it shows the other classes, but what I want you guys to see is that you can't just haphazardly choose any 3 angles that you want, okay, or any 3 letters that you want. Let's say I give you something like this. Let's just create that triangle and look at that angle, and that one. And now I'm going to try to see if I can go dilate. Would you guys agree that those 2 triangles are non-congruent? Okay. But, let me color it so we talk about it a little easier. Got the red one and the blue one. But if I ask for that angle compared 56, both of them are 56.83, right? If I look at this angle down here, 93.63, like this one here, right? And then, obviously, then hopefully this one turns out to be 29.54. Right? So does that show you that if I went angle, 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 I don't get congruency? That make sense? Okay, so that shows you hopefully that just haphazardly choosing any letters that we want, you're not going to get congruency. And we'll talk throughout the week which order of parts we need so that we do guarantee congruency. Yeah.
Would an angle would be the only configuration that wouldn't work?
No, side angle doesn't work either.
All right.
But the other 4 do. So what happens here, guys, is eventually, okay, guys, I don't care about the windows, okay? What happens eventually is that we get into talking about what is the relationship between these 2 triangles. If they're not congruent, they're incongruent, right? Okay, but there's a relationship. You saw that I dilated those, right? So that means these 2 figures are similar. So AAA is actually a similarity postulate, not a congruency postulate. And those are things that the rest of the course is going to kind of target for understanding congruence and side, angle, side, angle, angle, side, and angle, side, angle as we move on through the next couple of days is going to allow us eventually to be able to understand this a little bit better. Does that make sense? Like I need us to understand that you cannot just haphazardly take any of the components, sides, and angles and list them as a group of 3 and get congruency from that. Okay, there's a predefined structure that we need to abide by. Okay, I'm going to open up an assignment in Math Excel 4.2. It's not due tomorrow. It'll be due Wednesday, but there's probably going to be homework on top of it tomorrow. Okay, so probably don't want to procrastinate too much on that.